Okay, so welcome everyone to our STEM's hybrid event. It's a pleasure to introduce Dr. Joel Leja. So Joel Leja is an assistant professor of astronomy and astrophysics at Penn State University, and he holds the Dr. Keiko Mia Ross Early Career Endowed Faculty Chair. So Joel's research focuses on understanding the processes of galaxy formation through combining modern deep galaxy surveys with telescopes like JWST with statistics and machine learning. So in particular, he specializes in modeling observations of distant galaxies and in data-intensive astrophysical methodologies. Joel received his PhD in astronomy at Yale University, and he was awarded the Yale University's Brower Prize for PhD thesis of unusual merit. And more recently, Joel was named a Clarivate highly cited researcher both in 2023 and in 2024. So he's among one of the top 1% of most cited researchers in astrophysics. So today, Joel will talk about rapid inference of galaxy properties in the age of deep and large-scale surveys of the universe. So Joel, please take it from here.
Lovely. Well, thank you for the introduction. As you may have just heard, I come here, I study how galaxies form. I'm an astrophysicist at heart, but I'm here in front of you all for a good reason, which is that the field has completely changed since I started. I was telling some of you at lunch today, I did my thesis getting spectra of 7 galaxies near the edge of the observable universe at the time. And I wrote my own creaky analysis code. It took something like 100 core hours per object to slowly MC its way through all the physics we needed. That all worked at the time. But we live in a different time now. We're in an era, for my field in particular, where we're kind of mapping a large fraction of the observable universe for the first time. And so there's a huge amount of data coming in. My 7 galaxies that I spent several nights observing for, now we can get 3,000 galaxies at the same time with one set of observations, and we get something like 10,000 galaxies a night. So if I were to go back to the same facility nowadays, those 7 galaxies would be something more like 50,000 galaxies. And so I'm not that old. This was a decade ago. Things have blown up quite a bit. And so we're trying to catch up with our inference methods. And I think our inference methods are catching up too. And I'll tell you some of that today. That's kind of my goal. But just to give you a sense, this code I wrote to try to analyze distant galaxies and understand what's in them, we couldn't really use it. It was too slow. So to analyze a modern survey, we had to get very lucky. And we did. Harvard had a new supercomputing cluster and they wanted to stress test it. They had 15,000 cores and they said, can someone break this? And I said, yes, my code is slow enough to do that. I volunteer. And so I managed to get all sorts of exciting science done because I had access to the supercomputing cluster. I had a few million CPU hours, 5 to 10 million, which I had available to me. Now my grad student can do the same analysis in a couple hours on his laptop. And so that's how quickly things have moved. And so doing the same thing faster, though, is kind of boring. And I'll also talk about some of the new things we can do with these data-intensive methodologies and some of the things we worry about. And so that's kind of a broad overview of where we're going here. I will start with a few pictures of space. So this is the Hubble Deep Field. Most likely the most influential picture that has ever been taken by an astronomical telescope. I won't claim it is, but to me it probably is. And so every point of light you see here is a distant galaxy. There are probably thousands of galaxies here. And one of the first things you want to know when you're studying astronomy is distances. How far away is everything? So here I've circled every object, and every object has something called a redshift, which is a metric for how far away it is on a cosmological scale. It's also a sign of how far back you're looking in time. But there's actually a ton more information here. It's not just distances. Each of these little objects has billions, tens of billions, hundreds of billions of stars. And all of those stars have their own formation histories. And so we have a lot of questions, a lot of things we can learn about these deep images of the universe and the galaxies that are within them. And we want to learn how many stars are there, what kind of heavy elements are in them, what kind of cosmic dust is between us and them. And we can learn all sorts of stuff about what they are. These are really cosmic ecosystems. There's a lot going on. A galaxy is like a gas factory, but everything baryonic in the universe, almost everything, happens in these systems. So there's a ton of physics. That's one of the main modeling challenges, is how many different physical processes are going on. And these galaxies are also the sites of all sorts of other extreme physics that we really want to learn about. And so they are the site of much action in the universe that we care about, and we really want to understand them, not just how far away they are, but what's in them, how they came to be, why they're here. And there's also the understanding of why we're here, which is ultimately tied to the birth of these galaxies and their growth over time. And eventually they produce things like humans, so that's kind of interesting too. And so what do I do exactly? Well, I take these beautiful images of galaxies here. This is our neighbor, the Andromeda Galaxy, across the electromagnetic spectrum. And I turn these things into even more beautiful numbers, and very important numbers. Things like their mass in stars, or their formation history, or how many heavy elements are in each galaxy, how many supermassive black hole, or the properties of their supermassive black hole at the center. And this is the kind of data we're working with. This is actually exquisite data. I'll show you more typical data for a distant galaxy in a second. So, like I said, this is Andromeda. It's gorgeous. This is what I work with. Okay, this is a distant galaxy. This is at redshift 2. The universe was about 2-3 billion years old at this point. But you have much less information. And sort of the heart of the problem is that you know very little about these distant galaxies, but there's so much going on in them. So how can you reasonably, accurately extract information about these systems and do it on a huge scale, because we have so many maps of the universe at this point. And so these are just pictures of the same galaxy at different wavelengths. And you see also the characteristics of the data change quite a bit. And we have a lot of beautiful spatial information here, and this is just a blob. And so you want to kind of deal with this in a sensible way. Right now, all we do, we take these beautiful images of distant galaxies. Not so beautiful, blobby, I guess. We actually throw out most of the information here. We draw a big circle around them. We say, this is the galaxy. We add up all the light, and then we just fit the sum of the light. We ignore all the stuff we see. That's because of computational limitations. Good. We live in an exciting time for my field, thanks to kind of decades of investment from NASA, from the NSF, and from ground-based and space-based facilities all over the world. We have wonderful data for distant galaxies. There's a handful of things called deep fields, where basically many telescopes have pointed for a long time at these deep fields. They're often blank spots in the sky. You don't see anything else. And so they're great opportunities to stare until you find something that's very far away, like a distant galaxy. And so we have this lovely information all the way across the electromagnetic spectrum. Each one of these points comes from an image. We've added up all the light for a distant galaxy and summed it and given it here a little uncertainty, and then we fit models to it. And so imaging data is very useful, but it doesn't tell us that much in the end. And what we really want is spectroscopy. Spectroscopy spreads the light out, and you get to see all of these very information-rich absorption and emission features, and from different atoms of different types. There's a bunch that are labeled here. And in brief, these usually come from the atmospheres of stars or nebula, and they can tell us what kind of stuff the galaxy is made of and how old its stars are. And so this spectra are super useful, but they are much more expensive than photometry. And we can only afford to take spectra of a few % of the objects that we can take images of. And so the game is to try and calibrate our models using this very informative data and then apply them to much less informative data that span the whole sky. The best case scenario, this doesn't happen too much, but well, okay, it happens sometimes, but best case scenario is when you have both photometry and spectroscopy. They give you different types of constraints. That's lovely, and being able to jointly model these is very useful. It is an ongoing challenge in the field, though, that spectra have thousands and thousands of pixels, whereas photometry only have a few data points. And so calibrating these two very different types of data against each other, you throw them in a likelihood function, often the spectrum will dominate. That's something we're working on. Anyway, Bayesian inference. happens to be fantastic for this particular problem. Why? Well, here the posterior is always a compromise between your data and your prior, right? That's what Bayesian inference does. If your prior didn't matter, you have kind of a data-dominated problem. You don't need Bayesian inference, not really. Your data tell you the answer right out of the gate. You can write down any prior you like, it's dominated by the data. Okay. Conversely, you can imagine a prior-dominated problem where there are no data, really, or no data that tell us anything. It's kind of a theorist problem, right? It's for people who think about things. Galaxies are a great example of where Bayesian thinking is very useful because the data are only weakly informative. They only tell us a little bit. The prior matters a lot, right? So every answer is always a compromise between these two things. And the trick is you need to choose a good prior. But to choose a good prior, you really need to know what's going on. And that's what we're all struggling to do to begin with. And so this is a very useful way to think in my field. This is just a little example here. Don't look at this too closely, you'll go mad, but over here, I'm just adding more and more images of a galaxy. And then over here, we're learning more and more about this galaxy. And so as we add more data points, our posteriors for each of our physical parameters start to collapse and they start to head towards the truth. And so here we're fitting something like a 20 parameter model, and I've collapsed it into a few physically informative parameters here. The details don't matter that much. What I want to convince you with this slide is that the universe can be and is effectively arbitrarily complex. And so our goal as people who want to learn about that complexity is to simulate the correct physics. As long as we can simulate the correct physics, we can marginalize over those physics or measure them or whatever we need to do. As long as our inputs are good, our outputs are good, even if our data isn't very informative. Right? That's the goal. We want good inputs. Can we do that? Hey, do we have enough information to start asking these questions? Well, I'll show you some dirty laundry from my field. Okay, this is just an example, a coding challenge. Okay, so this is a galaxy modeling experiments. What we did, we took beautiful data, and so exquisite, identical, high quality space-based data. We asked all of the people that do this work, and in this case, we got 13 groups to do this, to just model those data and tell us what came out. Hey, what are your different codes telling us about the universe, about these galaxies with this perfect, excellent, high quality data? Feeding in all imaging data. Okay, so we did it. Here, these are 13 different plots. There's a line in each plot. That line is drawn in the same way and it's not a fit to the data. And all these points are different galaxies at cosmological redshifts in the deep universe. Right? And so the y-axis is the logarithmic current star formation rate, and the x-axis is the logarithmic mass of that galaxy. And I set this all up. Don't worry about the color coding, it doesn't matter. The point is, all of these galaxy populations look very different. And keep in mind, these plots span something like 4 or 6 orders of magnitude. And so if you see different clusters of different points in different places, we're talking about factor of 5 differences, factor of 10 differences, they're big. And all of these different galaxy populations revealed by these different codes, they imply very different underlying physics. And I'm not going to march through all of this stuff. It would take a while, a whole lecture, but these galaxies are dead. How dead are they? It matters a lot. How quickly are they dying from the star forming population? It matters a lot. Some of these codes say they die very quickly. There's nothing in between. Others say it takes a long time and you see stuff in between. These are very different pictures of the population itself. None of these people are doing bad things. None of these people are doing wrong things. These are all smart people making reasonable choices. But the problem is there's so much stuff going on, we get different answers. Okay? So why? Why do we get such different answers for the same inputs? Well, I'll take you through some of our problems in this field, some of our challenges. The biggest and most fundamental one is something we call the outshining problem. Okay? So distant galaxies are nearly point sources, not always. Often they are, or when they're not point sources, they're barely resolved. And so we're kind of jamming all sorts of physics into this very small source about which we have very little information. And so we're adding up all the light from all the stuff in that galaxy, and that light is added linearly. Maybe you see the problem already. Things in astrophysics have very different luminosities, they have very different brightnesses. So if you're just adding the light linearly, well, you end up seeing just a couple things. In our case, mostly what we call O stars, very young, very bright stars. They put out a majority of the light. Sometimes it's a accreting supermassive black hole that puts out the majority of the light. Most of the time, you only see one or two things in these distant galaxies. They dominate the light. And you have to infer the existence of the great majority of things that are not bright from these little breadcrumbs, these little clues. And it's very difficult. And so in this case, most of the mass in galaxies is in dim, low mass stars that we will never see at cosmological distances. And most of the light comes from a handful of very bright blue things. Okay, so here, this is a picture of the Andromeda galaxy. Maybe some of you have seen it, maybe not, I don't know. If you look up in the sky and see Andromeda, it's basically a point source with our eyes. But here's the true size of Andromeda compared to the full moon. It is massive. It actually spreads out all across the sky. And this is kind of the same problem we have. What do the bright things tell us about the rest of the system that we can't see at all? And so the outshining problem, this is a huge issue for our field. We just don't have the data about the stuff we want to see. Another one you may be very familiar with. Right? So I won't spend too much time on this, but there are strong degeneracies in our data. A lot of the stuff we want to learn has the same effect on our data. Okay, so if we add a bunch of old stars, or we add a bunch of cosmic dust, or we change the rate of heavy elements in the system, they all kind of have the same effect on the imaging at least. So we need to find some way to sort out the difference between the two effects. Okay, all right, so these are problems for imaging. Fine. What about spectra? Spectra are much more informative, right? We have thousands of pixels. We have all these sort of rich absorption and emission features. Images can't tell us the answer, but maybe these beautiful spectra can. Here, these are some spectra from probably just about the best spectra we'll ever get of distant galaxies. These are heroically taken. They take 20-hour exposure, so over multiple nights, they'll point at the same thing, just go very, very deep on some of the best telescopes in the world. And so we have these incredibly high, I mean, for an astrophysicist who does what I do, a signal noise of 50 is effectively an infinite signal noise. Okay, remember I was talking about a factor of 10 uncertainties earlier. It's a factor of 2%, that's incredible. Okay, we'll probably, I think it is doubtful we'll ever get anything approaching this data quality in my career again. It was a huge investment. I had something called legacy. Right? And so what if we have these data? What if we do the same exercise? They have some people run their codes on it, compare the outputs, and we get the same answer this time, right? Alas, this is code 1 versus code 2, and then code 2 versus code 3, basically. And this is for the so-called metallicity, so the abundance of heavy elements in the system. This you should be able to read right off of the spectrum. It should be straightforward. And what comes out of these different codes is effectively a scatter plot. There's almost no one-to-one correlation here. And you could do the same process for something called the light-weighted age. This is the easy way to estimate age. It's the age of the light hitting your telescope, so you don't care what you can't see. It's just the age of the light that you can see. You have a little bit more one-to-one correspondence here, but there's a ton of scatter, and there's a ton of offsets, and there's a ton of weird trends as a function of age. None of this, you don't want any of this. Okay, so I just told you this is probably the best data we'll ever get. And here we are. All of our analysis methods disagree. So I return to the same question. Why? Why is this so hard? And so the challenge with spectra, with this information-rich spectra, is something else. I think basically, I told you there are a ton of physics in these systems. We do not include most of those physics. When I was starting grad school, we would fit 4-parameter models to most distant galaxies. Now we're up to 15 parameter models or so. That is still incredibly insufficient to describe the light that we see. There's just not enough in there. So we come to this old adage, all models are wrong, but some are useful. How much physics do we have to cram in for our models to be useful? I'm just gonna play a little movie here showing you all of the physics that I worry about on a day-to-day basis. I've taken out the things I worry about on week or month time scales. Okay? So here, thing we care about, effect on the data. Oh, the movie cut off, but that's okay because the list never ends. Cut off, all right. We don't want to be here forever. This is a hard problem. There's too much going on. Okay? So the models right now, they just don't include enough physics. Okay? Why do they not include enough physics? Well, part of the problem is we don't know the physics. I'm not going to go into this slide too much, but these are basically the formation histories of different galaxies in different simulations of the universe. And the problem with simulating the growth of galaxies is the gigantic scales involved, both in space and in time. They force approximations. You can't, the computers are not fast enough to do this. And so because there's approximations, you get the same problem. Reasonable people make reasonable but different approximations, and the outcomes become totally different. So these are 8 state-of-the-art simulations of galaxy formation. All the galaxies behave differently. Which one's right? I don't know. And so these emergent physics, we just don't know them yet. And so maybe now you start to see the problem. There's a ton of physics. We don't know them that well. The data don't tell us that much. And we only see bright things to begin with, not most of the stuff we want to see. And I'm not going to talk about selection functions, but that's also a major statistical challenge as well. Good. So where does that leave us? Bayesian inference. I told you it's powerful. And now maybe you also believe it's dangerous. It's very easy to get the wrong answer. So we all know this. All models are wrong, but some are useful. What are they useful? And useful for what? And what does useful mean? Well, for us, as a scientist, my goal is to create new knowledge. I want to learn something about the universe. That means we need to understand a lot in order to produce new knowledge. Right? We need to understand our measurement uncertainties, our instrumental effects. Probably the hardest part is we have to have reasonably accurate generative models for what we're fitting, stars, gas, black holes, so on. Okay. And if these things aren't true, be careful. Modeling can do a lot more harm than good. And you don't want to be overly convinced in your own models. That way lies madness. Okay. So can we do well enough? Okay. Can we make progress on this problem that I just spent so much time convincing you is very hard? Yes, actually, yes, we can. So there's been this old problem. I'm not going to go into it too much, but basically, galaxies seem to produce way too many stars in the early universe, when the universe was 3-4 million years old. This problem has been around for a very long time. The simulations say you can't produce that many stars. You'll have way too big of galaxies later on. But we keep finding this problem. 0.4 dex is a factor of 2 to 3 offset from what we should be finding. Okay, so part of my PhD thesis was trying to solve this problem by cramming more physics into our models. So we went from a 4-parameter model for distant galaxies to a 15-parameter model. Okay, and in the process of doing that, we added all the right physics. We added enough of the right physics. Actually, probably only one piece really mattered for this, but it doesn't matter. And we were able to finally get agreements between these two measurements, the simulations and the observations, by putting more physics in the model. Right? So we can solve things. This is not hopeless. It's just very hard. Hey, this was a big, large-scale problem. We got good agreement with the simulations. We fixed this. But this was computationally expensive, as I said. This was 5 million CPU hours on Harvard's supercomputer, actually. I mentioned this already. And there are many puzzles that remain. Right? So what's the next step? How do we do this better? The fundamental problem with adding more physics is something called the curse of dimensionality. You might all be familiar with this, but as you add more dimensions, your gridding or your system becomes unfathomably large. And by the time you reach a 15-parameter model, you need something like a Google data center to hold all of your models. Well, we think we need hundreds of parameters for any given galaxy, so the curse of dimensionality is a real problem for us. The solution: on-the-fly compute. You generate every model exactly when you ask for it. That works, but it's very compute intensive. You end up with something like 15 hours per fit. And so that's how we get to this point of needing several million CPU hours to analyze a deep field. Why is it so slow? Well, it's pretty simple. You take your galaxy observations, you need to build a model. We spent a lot of time optimizing this. So much physics goes into this model. You don't need to read any of these words. Physics. okay? But it's very expensive. You can generate about 20 models per second, and that's after many years of optimization, much of which I was doing on Fortran code. Okay, you can't really go faster than this, not in any sensible way. Well, you can generate 20 models per second. It takes about 1 million models to get a good estimate of the posterior. And that's how you get here, 15 arrows per object. Okay, so what do? Well, one thing we've been doing recently in the last couple of years, a neural net emulator. Okay, we have all these fancy physics. They're all written down very well. Who cares? Okay, it's basically a black box. You put in parameters, you get out observations. Well, we can replace that black box with a neural network, and we can speed up this process by quite a bit. Okay, so speed it up by factors of 100 to 1,000 or 10,000 on a GPU. And it's a bit scary for physical scientists to have models suddenly that have their own errors in them. It's upsetting to people. So we spent a lot of time ruminating on this. Can we still get good answers when our models have errors that we put in ourselves? And that's the trade-off with these neural nets. They're fast, but they're not precise. So this was led by my grad student, Leja Matthews. So we spent a lot of time thinking about this trade-off between, if you have a larger neural network, you produce better results. They're more accurate, they're more fiducial to your input model, but it takes longer to execute. So at some point, your model becomes just as slow as the original input physics, and that's actually not that far in. So we have to find some trade-off that it's fast enough to be useful, but doesn't produce so many errors that we can't get a good answer. And so here, these are just a bunch of different networks of different sizes that give different precisions as a function of wavelengths. And so this is the trade-off. And we have to allow some amount of uncertainty. It turns out the uncertainty that we found was something like less than half of the measurement uncertainty. As long as our neural networks are that precise, we're able to get pretty good answers. And this was the output. This is mass, mock data versus, and over here is dust. And just stuff we want to learn about in the universe. And so we tuned this up and down until we got a speed up of about 100 to 1,000. And we're still able to get these excellent answers. And so this was very satisfying. Neural nets can do everything much faster. And not only are they faster, they're also differentiable. You get these nice automatic differentiation outputs. And so that unlocks a totally different type of sampling, these gradient-based samplers, which are much more efficient. I'll just go through these quickly. You may know this already, but trying to find the true solution on some complicated likelihood surface. Okay. A random walk sampler is normally stumbling around, a little bit drunk, can only probe the height of the hill you're climbing at any location. But these gradient-based samplers are much more efficient because they can also probe the slope. You can head directly for the true solution, as long as you don't have a multimodal posterior, which we do, of course, but let's not worry about that right now. Good. So we have efficient gradient-based samplers, and we have this raw computational speed up of factors of 100 to 1,000. Amazing. And so we can go back and we can do much better science. So here, this is one of Webb's first deep fields. We found all sorts of treasures in here. Rachel Bezanson was the PI of this program, Uncover, actually. She's over at Pitt. We work a lot with her. And so one of the great wonders of this work is that I told you it took Harvard supercomputing cluster to measure the properties of these 100,000-ish galaxies in this field. Well, now, when we got these data from Webb a couple of years ago, my postdoc, Bing-Ji Wang here, could do this work on a modest compute allocation in a couple of days. And so we can start really discovering some exciting things in here very quickly. And that was awesome. So we discovered all sorts of things here. There was the second and fourth most distant galaxies ever seen, actually. So we found those and we published them because of these neural net emulators. They were very fast. They let us learn this all very quickly, turn around, ask for more data, find the right objects, and discover some record-breaking things. But going faster, well, it's kind of boring in the end. It's good to go fast, but you're doing the same kind of science. We can also do new things. We can do qualitatively new things, and that's maybe the most fun part of this analysis. What can we do that's new? What couldn't we do before? Back to this problem. Hey, I told you for distant galaxies, we just kind of draw a circle around this. We add up all the light. We don't care about how it's distributed. We're actually throwing away a ton of information. We're saying they're unresolved and they're not. And we know what these things look like. You can see little spiral arms here. You can learn a lot about a system. But we throw out that information because frankly, our codes are just too slow to do anything about it. So in principle, you could fit every pixel. This has a ton of advantages. I will not go into them. We'll be here for a long time. Just trust me, this would completely revolutionize the way we do astronomy. We could just fit every pixel instead of going through this long, complicated, ultimately wrong process of throwing out enough data so that our models can fit those data. Okay. So why haven't we done this? Why don't we just model the images instead of adding them all up to make a single data point? Well, it's a hard problem, okay? These pixels, they're not independent. They're all smeared out by the point spread function. So every pixel is correlated with adjacent pixels, necessarily. Okay? Just from physics, just from the way detectors work. So if you want to try to model every pixel in one of these galaxies, you can't just model every pixel independently. You have to model all of them at the same time. That's a very hard problem because each pixel has its own many labels of the physics going on inside of that pixel. Okay. I told you one of the fundamental problems in the field, you can ignore everything here except for this picture. One of the fundamental problems in the field is outshining. The bright things outshine the dim things. We never see the dim things. That's not strictly true. This is an image of a distant galaxy from the James Webb Space Telescope. If we added up all the light in the system, we would basically only see these few blue splotches, which are way brighter than everything else. But if we can model all the pixels as they are on the detector, we see directly all of these old stellar populations, the things we're looking for. And so if we can do this modeling, we can solve one of the fundamental challenges in my field, outshining. So that's very promising. And so this is something we've worked on. We have this new approach, it has a fancy name, Pirate, but the idea is you forward model everything. You can fit images of any resolution and you get out some picture of a galaxy and all of its beautiful spatial complexity. Right? Every pixel has its own population of stuff that we care about. Right? This is doable through these beautiful derivatives. They're very nice. It powers this hyper-efficient Hamiltonian Monte Carlo sampling. And so what we can do is take something like a 75 by 75 pixel image with 20 filters, imaged in 20 different bands. And we fit every pixel on its own with its own complicated 15 parameter model. Well, 75 times 75 times 15 is about 84,000 parameters. We've come a long way from the 4 parameter models I was talking about just a little bit ago. And this would take something like 100,000 core hours with classic fitting, but now we can do it in about a day on a GPU, or even faster now, actually. This is sped up since I wrote this slide down. So this is exciting. Does it work? Yes and no. You can get these beautiful maps of these distant galaxies. This is just a galaxy in a deep web image, and here's the map of the mass from that object using this technique. And it's beautiful. There's a lot of information. You can do the same thing with other parameters. This is a map of the heavy elements. You get out very sensible answers, actually. This makes a lot of sense. You're an astrophysicist who does this work. You look at this map and say, oh, yeah, that's what I thought. Yeah, that's probably about right. And, excitingly, the things we want to measure, all these fits also give out much more precise answers for what we want to measure. The typical uncertainty for the mass of a galaxy in the distant universe is something like 20 to 50%. These spatially resolved fits give us something like well-calibrated uncertainties of 5%. So the stuff we want to measure, we can measure much more precisely. Cool. Okay. Who cares about this? You need to model the smearing of the light, otherwise you get the wrong answer. It's the summary here. I'm not going to talk about it. Great, this all sounds good, Joel. What's the catch? Something's wrong, right? Yes, something's wrong. Before we can apply this at large scale, we have a fundamental problem. This is an observed galaxy. These are 5 different models where all we've done is play with the small scale correlations between gas, between dust, between stellar populations of different ages and abundances. We just tweaked them. We don't know what they are. We build these codes to know what they are, to learn them. So we don't know what they are. They're priors. So we have 5 different models, 5 different priors. All of them produce beautiful fits of the observations. And the output things that we care about, in this case, the stellar mass, they're different by factors of 4 to 5 between all these different models. And so this is a bit of a challenge and one we're still working on. This is a hard problem. The answer kind of depends on stuff we can't see. The small scale physics of dust and the dynamical mixing of stars at different ages and heavy elemental compositions. So you need a very smart prior to do this. We are in search of this very smart prior. It's also a highly multimodal problem. So HMC is sort of ill-suited for it because it tends to get stuck in these little local minima. So that's a challenge you can work around, but it takes some cleverness. Ongoing challenge. Would be fantastic to solve it though. This would really revolutionize my field. I'm not kidding. A lot of the machinery we use day to day would be replaced by this type of work. So it's a problem worth doing, I think. Good. That's imaging. And what about spectra? I told you spectra are very informative. They're also a very cool thing to focus on right now because we are in the age of mapping the observable universe, a large fraction of it with these large spectroscopic surveys of the universe. There's a ton of capital investment that has gone into this. This is mostly for understanding dark energy, a huge problem in physics. As a beautiful side effect, we get all of these lovely spectra of distant galaxies. And so it is kind of a golden age for my field. Okay, we have all sorts of large surveys of the universe. This is just an example of some of the spectra we get from a survey I'm involved with, PFS. They're lovely. These are objects in the universe which is 2 billion years old. We can learn all sorts of things about them. And so we've gone through this process of building neural net emulators also for spectra. There's some advantages of this. You don't need to worry about cosmological redshifting. You can do it in a rest frame. There's some disadvantages. The data are much more complex. The physics are much more complex. But we can do it. So this is something one of my grad students, Emily Burnham, is working on right now. We're trying to emulate each step of the process now, not do everything in one shot like we did with imaging. There's just too much physics to put in. So we're building a bunch of different emulators for different parts of the physical models. For example, nebula in astrophysics, they're powered by nearby young hot stars or supermassive black holes, and they have their own pattern of emission. So that's handled by something called a photoionization model. Photoionization models are very complicated. There's hundreds of parameters, and they take a long time to run, 2 minutes per model. So you can't really use them in an inference loop. Okay. So Leja here, she's one of my students, she's just graduating. She built this emulator for one of these problems, one of these codes, Cloudy, and we can get out all sorts of very nice nebular models with an arbitrary thing that is powering the nebula. Okay. And so this predicts a ton of data with pretty good uncertainty. It does it very fast, something like 10,000 times faster than the original photoionization models. And we can either use it to marginalize over stuff we don't know, happens a lot in astrophysics, or if we have really good data, we can learn fundamentally new physics about what's ionizing gas, what's powering these nebulae. Okay, so we have a few different physical components, all of which we've built emulators for that go into this model. There's also the stellar component. You can emulate the stellar spectra on their own. These are decades or centuries even of people working on stellar evolution, what stars look like, what they turn into. And we can wrap a beautiful emulator around them. This works very nice. It produces uncertainties of about 0.1% in flux space, which is way smaller than our typical observational uncertainties. And so this problem seems to have been pretty well cracked. So this is awesome for us. This is an example of the scaling. Here in red, this is the way we normally do it. Okay, so how many spectra can you predict at the same time? And in blue, this is if we put our neural net emulator on the GPU. We can predict many spectra simultaneously. We get this sublinear scaling, which is awesome. And so we can model tons of galaxies at the same time, and it's something like 100 times faster overall. So we also get these additional speedups from gradient enhanced sampling. This means we're about ready to tackle these large spectroscopic surveys in the future. But again, it's a bit boring to do something old fast. What kind of new science can we do now that we have this new methodology that's much, much faster? it unlocks fundamentally different science questions. I'm going to come back to this problem, this thing, bursty star formation. Galaxies kind of get brighter and dimmer based on whether or not they formed stars recently. This is a very annoying problem because when we look at things in the sky, we only see bright stuff. So if you're lucky, you happen to be catching a galaxy while it's bursting, it's going through this large burst of star formation, you can see it. But most galaxies may be orange, and they're below the detection limit. And worse, all these recently formed stars, they all kind of look similar. If you imagine here, this is a star formation history. This dash or this dotted line is the true star formation history, and you see it going up and down and up and down and up and down, burst, quench, burst, quench, burst, quench. We try to fit the data from this galaxy. We can fit it to perfect precision, 1% precision. And our answer here in purple has no bursting at all. It's a steady increase in star formation rate. And these are statistically identical solutions. There's just not enough information in the data. Hey, well, we told this model that there's no bursts going on. What if we tell the model, hey, there is bursty star formation. We know about this. Okay. Well, it says, great. There was one single burst and nothing else happened before this. Hey, it's very happy to be very wrong. This is pathological. This means you can fit the data perfectly and be terribly wrong. It's very frustrating. Causes all sorts of problems. What do we do about it? Well, fitting a single object is degenerate, but if you fit a population of objects, you fit everything at once. You catch all these phases of up and down and up and down. You can constrain the timescales for the whole population at the same time. Normally, that would be heinously expensive. You need to generate hundreds of millions of models in order to do a whole population at once. So, with neural net emulators, I told you we can generate now something like 2,000 model spectra every second. Maybe you can feel the wind in your hair moving pretty fast. It's just not nearly fast enough, even to do this problem. You need something like 500,000 to 100,000, or 50,000 to 100,000 model galaxies to propose one population. You need probably 1 million populations to do a whole population fit. Takes too long, 10,000 core hours. You can't do it. So what do? We replace everything with a beautiful black box simulation-based inference where we can amortize these calculations and we can do this population level analysis much faster and much more efficiently. I'm going to skip over some of these details, but in brief, we spent some time collaborating with Ashley Villar and Josh Spiegel, thinking about how to modify simulation-based inference to deal with some of the problems we have in astronomy. Our uncertainties are highly heteroscedastic. We often have missing data. Okay? And in both cases, SBI won't work. Okay? So we spent some time thinking about how to use SBI as a simulator to solve some of these problems. We have this method called SBI++. It takes a bit longer if we have missing data or out of distribution data. But we can run SBI on it, and so that's very useful. We can use it for astronomical problems. Okay, so I'll just show a little example of this type of modeling, population modeling. This is led by my student, Emily Burnham. Okay, so the idea is that we propose populations with bursty formation histories, up and down, up and down, up and down. So here, we just have a few, this is a toy problem. We have an amplitude of the fluctuations. Okay, how big is the burst of star formation? We have a time scale for the up and down fluctuations. How frequently does it occur? And what is the period? Okay, and then we have a long-term slope. What is the long-term average of the star formation rate? Is this galaxy forming more and more stars over time or less and less? Okay, so these are our 3 population level parameters. Okay. Excuse me. And the idea is all these other things we want to know about galaxies, and we just marginalize over them. We generate tons of different possibilities for cosmic dust, heavy elemental composition, etc. All these other physics. We're not learning them. We don't care about them. We try to marginalize over them. And so we generate all these different populations. Right? And then these populations will have different distributions of observables. Okay, the things we observe will look differently. The histogram, the whole population will look differently, depending on the different types of bursts going on in these systems. Okay, that's the basic idea. Does it work? Okay, so simulation-based inference for galaxy population modeling. As someone who has thought about this problem for a long time, it has felt very intractable. I have been blown away by how effective SBI is at this problem. Okay, so we're able to take distributions of observables and turn them into true, accurate, well-calibrated results about the bursty input population. Okay, and so we can accurately recover all these things that we've only speculated about before. Okay, things that we just haven't had the pieces. We're not able to put them together. Now we can actually model the observations as they are. We can learn real things about galaxies. And so we can constrain with just 500 objects, okay, not that many. We can constrain things like the long-term star formation history, the timescale of these bursts, and the amplitude to within a few percent to tens of percent. Totally undoable before. I'm not saying we've solved a fundamental physics problem, not yet. There's still this problem of not knowing the underlying physics in some ways. So there are some things we need to test. Say, what if we don't know how stars work? Or what if our formation histories are too simple? So we have some systematic tests to do by comparing to simulations. But this has finally the promise of solving some of these fundamental limitations in my field. I'm super excited about this. Okay. So second to last slide. I just want to try and convince you how cool this is for someone like me. Okay, so I cobbled together my galaxy fitting code with collaborators in 2017-ish. Okay. I told you it took something like 100 core hours to fit one object. Very slow, very painful. No one liked it. Hey, you don't want to put in a bug. You have to wait another 100 core hours to fix it. I spent much of my postdoc optimizing code, moving bits and pieces around, spending months with factors of 2. And after this, we were about as fast as it's ever going to get, something like 20 core hours per object, and we were quite happy with that. And this was 2019, 6 years ago. Well, things move fast. We learned about neural net emulators, okay? And so by 2021, we had replaced a lot of this physics with emulators, and suddenly we can do fits in 10 core minutes. Super exciting. GPU acceleration, auto differentiation, crank us down to something like 1 core minute per object. And then finally, of course, simulation-based inference takes somewhere between 1 and 10 seconds per object. So just to drive this point home, this is something like a factor of 10,000, 100,000, sorry, speed up in 5 to 6 years. This is completely game-changing. Not only can we do all of this physics faster, but we can also add in a lot more physics. And there is a lot of physics in astrophysics. Okay? We can fit things with hundreds, thousands, or tens of thousands of parameters. All we need to do is have reasonably accurate input models, and they already exist. All of these little pieces that go into the code, there's already hundreds of parameters that control them. So we can really cram all of the physics into these astrophysics, and we can fit everything in a reasonable amount of time. All of these data-intensive techniques. And it's all happened in the last 5, 6, 7 years. And so this has just been awesome for my field. Okay. So just conclusion slides. I won't read this. I'll leave it up. This is the last picture of Webb as it headed into deep space. Lagrange point 2. Kind of sentimental. But yep, that's it. Thanks, everyone.
Thanks so much, Joel, for a wonderful talk. Especially